So let's find the value of m which make the function v harmonic, or simply which makes the function v2 satisfy the Laplace equation. So here, v is given by x squared plus y squared plus z squared raised power m over 2. So let's find partial v partial x. So by chain rule, we differentiate inside the bracket, so we get 2x, and then drop the power, so which is m over 2, and then so you have to subtract 1 from the power, x squared plus y squared plus z squared raised power m over 2 minus 1. And by doing this, these 2 and these 2 cancels out. So this will be mx into x squared plus y squared plus z squared raised power m over 2 minus 1. So that is the derivative of v with respect to x. Next, partial squared v partial x squared. Now, this one is obtained by differentiating this function of partial v partial x. And because it has product of 2 terms, so let's call this one u, this one v. So by product rule, we'll have u prime v plus v prime u. So u prime, differentiating this part, we get m. So we'll have m into x squared plus y squared plus z squared raised power m over 2 minus 1, and then plus this part differentiated will have m over 2 minus 1. So drop the power, and then differentiate inside, we get 2x, and then you multiply by u, we get mx, and then now we multiply by this bracket, x squared plus y squared plus z squared, but then the power you subtract 1. So m over 2 minus 1, we get 2. So by doing this 2 cancels with this 2 here. But then remember, this is the same as 2 over 2, because m over 2 minus 1 the same as m minus 2. So this is you can actually extend this line and write m minus 2. So partial squared v partial x squared will be m into x squared plus y squared plus z squared raised power m over 2 minus 1 plus, this will give us m into m minus 2, and then x by x is x squared into x squared plus y squared plus z squared raised power m over 2 minus 2. So you factor out this power, this bracket with this power. So we'll have x squared plus y squared plus z squared raised power m over 2 minus 2 into brackets. So for this one here, we'll have m into x squared plus y squared plus z squared power 1. So that's 1 plus this will give me this term here, plus m into m minus 2 times x squared. That's what we have. Then, because this part here has an m and also this part has an m, so you can as well factor it out. And so partial squared v partial x squared, factoring out, will have m into x squared plus y squared plus z squared raised power m over 2 minus 2 into brackets. Now here, I can write this one as m minus 2, because I've already factored out m. Or let me just write this other part first. So raising to power 1 then is the same thing as just having m x squared. Okay, so factorization of m outside. Now m is not at this point, so just have x squared plus y squared plus z squared. Plus z squared, and then plus, this will be m minus 2 times x squared. So this we call it equation 1. Similarly, you can get the second partial derivative of v with respect to y and second partial derivative of v with respect to z using this structure of partial squared v partial x squared. So this will be m into x squared plus y squared plus z squared m over 2 minus 2 into x squared y squared plus z squared plus m minus 2. But now, because now this is with respect to y, so this would be y squared. Call this one equation 2. And then partial squared v partial z squared will be m into x squared plus y squared plus z squared raised power m over 2 minus 2 into x squared plus y squared plus z squared plus m minus 2. Now, because this is with respect to z, then here you have z squared. You can actually prove this result for partial squared v partial y squared, partial squared v partial z squared in a similar manner to the processes we have worked out to get partial squared v partial x squared. So adding 1, 2, and 3, we get partial squared v partial x squared plus partial squared v partial y squared plus partial squared v partial z squared will be. Now, one thing that you observe in all these three equations is that m into this bracket raised power m over 2 minus 2 is common. So I factor it out. M into x squared plus y squared plus z squared raised power m over 2 minus 2 into brackets. Now I have x squared plus y squared plus z squared, x squared plus y squared plus z squared. So this is common. So this x squared plus x squared plus x squared will be 3 of them. Y squared plus y squared plus y squared will be 3. Z squared plus z squared plus z squared is 3. So I can have 3x squared plus 3y squared plus 3z squared then plus. Now here also, m minus 2 is common, and then x squared, y squared, z squared. So I can write m minus 2 x squared into y squared plus z squared. And then with this, I can write this equation as m into x squared plus y squared plus z squared raised power m over 2 minus 2 into brackets. Now factor out 3 into x squared plus y squared plus z squared plus m minus 2 into x squared plus y squared plus z squared. And you see in this square bracket, I also have a common factor of x squared plus y squared plus z squared. So that will give me, factoring it out, I have m into x squared plus y squared plus z squared raised power m over 2 minus 2, and then x squared plus y squared plus z squared, can say raised power 1 into 3 plus m minus 2. So that's what we'll have. Now you see these two brackets are the same. So using loss of indices, m over 2 minus 2 plus 1, I get x squared plus y squared plus z squared. So this will be m over 2 minus 1 into, so 2 minus 3 minus 2 is 1, so m plus 1. But remember, this is equals to 0 since we have partial squared v, since we must have partial squared v of x, partial squared v, partial y squared, partial squared v, partial z squared should be 0. So this is the same thing as saying m is equal to m into m plus 1 x squared plus y squared plus z squared raised power m over 2 minus 1 should be 0. And because x squared plus y squared plus z squared is not 0, so then this implies that this product m into m plus 1 is the one that should be 0. And this implies m equals to 0 or m plus 1 equals to 0, which implies m equals to -1. Since m equals to 0 is not allowed. So therefore, the value of m, which makes that given equation to satisfy the Laplace equation, is m equals to -1. Hence, the value of m is -1. That is how we were to argue out the solution for that particular problem. Thank you.